We will start by simulating the operation of a simple 3-layer phosphorescent OLED consisting of an HTL, an emission layer and an ETL. We will compute an IV characteristics and the internal quantum efficiency depending on the voltage and the currents. And we will show you how you can use LightForge to analyze quenching and find bottlenecks in your device. You can see a sketch of the OLED in the top right. In yellow, you can see an emission layer consisting of a host material and a phosphorescent emitter, the ratio of 85 to 15%. Adjacent to the left, in red, you see a whole transport layer with a small injection barrier towards the emission layer. And attached to that, an effective electrode that will inject holes into the HTL. Corresponding on the right, you see in blue an electron transport layer and an effective electrode to inject electrons on this side. We call the electrodes effective electrodes because they basically have the transport levels of a injection layer, of a doped injection layer, which we could also simulate explicitly, but as it is much more numerically involved, we choose here the option to inject the charges directly into the HTL and ETL with a kind of artificial injection level, which we then compensate by applying an additional built-in voltage, which I will show later. The energy levels of the OLED are shown on the right in the table. The column HOMO levels corresponds to the ionization potentials, and the column LUMO level corresponds to the electron affinities. So these are the transport levels. So the difference between these two would not be the optical gap, but the transport gap. The excitonic properties of the different materials that we will define for the simulation are taken from so-called Exciton presets, which are collections of typical excitonic properties for a given type of molecules. For example, there is an Exciton preset for phosphorescent emitters, which will have a radiative lifetime of about a microsecond, a singlet triplet gap of 0.4, 0.3 electron volt, and so on. Other electronic properties like the energy disorder or the coupling between the different molecules we'll take as identical now for the simulation, but I will show you how to adapt all of these properties, also the properties for the excitonics. Now, without further ado, we will switch to the SimStack GUI in order to set up the calculation of this OLED. To do a device simulation using LightForge Monte Carlo, we start by locating the icon for the LightForge tool, and we drag and drop it in the workflow window. If we double click the LightForge icon, options for the device simulations appear on the right. The LightForge settings are grouped in 8 different categories. You can use the arrow button here on the top to see the categories which might be hidden. I will give a quick overview over the different categories now. In the general category, you set up the type of calculation. So you can do, for example, either a calculation of a bulk system with a full periodicity, or you can simulate a system with attached electrodes, and you can define which kind of quasi-particles are allowed in the simulation. In the I/O tab, inputs from other modules of NanoMesh software are managed. This tab is not required for standalone LightWatch simulations. In the Materials tab, you can define any number of materials of which you want to comprise your device. In the Device tab, you can define different number of layers and each layer individually. In the Topology tab, you define the connectivity between different materials, for example, thread transfer rates or charge transfer rates between two species of materials. In the Physics tabs, the physics of the simulation can be modified. This is something you generally do not have to do. In the Operation tab, you can set up the simulation parameters, such as external electric fields, temperatures, and also convergence settings for the calculation. The Analysis tab has some specialized analysis options which I will not talk about now. In the Resources tab, you can allocate the resources for the calculation. We start to set up the device simulation for a 3-layer model OLED in the General tab of the LightWatch Wano. We choose a device layout stack, which will automatically put one layer on top of another. Another option would be to choose manual. This is not recommended. For this, you have to define the location of the different layers in space manually, so you can have custom geometry like horseshoe devices or similar things, but you have to be very careful that the boundaries of the different layers are matched accurately. Under the option Set PBC, we can set up the periodicity of the transport simulation. We choose the option Automatic here, which for a stack simulation means the system will be periodic, perpendicular to the transport direction, but of course not periodic where electrodes are attached. By checking the box Connect Electrodes, we connect two electrodes to the system to inject charge. As we want to simulate the operation of an OLED, we require holes, electrons and excitons. Now we go to the I/O tab. Since this is a fully parametric simulations, we do not require any input from other simulations. So we are gonna not check this box, and we won't have to do anything in this tab. In the Material tab, we can define the different materials used in our OLED. Using the plus button, we can add additional materials. Now I added a material and I will give it a name. So the second material I will call host. The first material I will call HTL. The options for the different materials here are separated by this thin line. So you can see now that we can define these two materials here. We could also add a third material and so on. So now we will go through the different options which allow us to set up our materials. In the drop-down menu, Import Mode Transport, we can choose where to draw our material parameters from, which are relevant for charge transport. These are 3 different kind of parameters: EAIP, SIG and L. Sig is short for sigma, and it refers to the standard deviation of the energy disorder. L is short for lambda, it refers to the reorganization energy of charge transport, and the AIP is short for ionization potential and electron affinity. We see that in this drop-down menu we have groups of these parameters listed either under QP or under PAR. So if they are listed under PAR, that stands for parametric. This means we input all of these parameters manually here in this material veiner. Here we see we get a table where we can enter different values. If we choose an option where some of the values are listed under QP, that's short for quantum patch, this means that we will use parameters which are previously calculated in quantum patch, and we will just have to supply input files from quantum patch, from quantum patch, and Lightwatch will automatically draw the values from these input files. Since this is a purely parametric simulation, so we will choose here PAR, here AIP, sigma, lambda. Similarly, we have this drop-down menu input mode Exotonics. There are two options to choose from: preset only and ab initio plus preset. Preset stands for Exciton preset. An Exciton preset in this context is a collection of different excitonic properties. For example, there's an Exciton preset called fluorescence, which will have a list of excitonic properties like radiative lifetime, thermal lifetime for thermal decay, intersystem crossing rates, and other parameters. This means if we choose preset only, all the excitonic properties will be read in from this preset. There are different kind of presets. For example, there are presets for typical fluorescent compounds, for typical phosphorescent compounds, for TRDF emitters, and so on. And these presets can also be modified, which I'm gonna show later, or you can make your own presets also. The second option, ab initio plus preset, allows to read in calculated ab initio parameters for different kind of excitonic properties, which were calculated using the Exciton preprocessor. Values which cannot be calculated within the Exciton preprocessor are then drawn from the preset. The preset itself that is used is chosen here in this drop-down menu preset. So for the HTL, it would be like we will use the fluorescent preset. This table with the title energies shows the parameters which are to be put in manually. So if we have here chosen parameter EA, IP, sigma, there will be 3 rows here for all 3 of these values. Then we have to supply values both for IP, for ionization potentials, and for EA, for electron affinities. So these are the mean values for IP and EA. So I put in here the values for the HTL, which we defined earlier. All of these are in electron volts. I will now continue to set up the different materials, which we saw earlier in the PowerPoint presentation. However, I will not record how I put in these values. I did this previously, so now we already have here the finished material definitions. So we see we have 4 materials, 1, 2, 3, 4, with the different energy levels as we want to have them for our model OLED. To modify Exciton presets, you can here check the box, show Exciton presets, and then you can go for example to the fluorescent Exciton preset. You see all kinds of entries, and you can, for example, modify the singlet decay rate or these other parameters. If you use also ab initio input from the Exciton preprocessor, many of these parameters will be ignored, as data from the Exciton preprocessor has priority over values provided in presets. For example, all these quenching rates, they can be calculated from data from the Exciton preprocessor. You can also define your own preset by pressing the plus button here, giving it a name and inputting the values that you want. For this OLED, we chose the same preset, fluorescence, for all material except for the phosphorescent emitter, for which we chose the preset phosphorescent, which will have a much higher inter-system crossing rate, and it will have a much higher radiative decay rate for triplets. Now with the materials defined, we can set up our device. For this we go to the Device tab. First, we are going to define the device cross-section perpendicular to the transport direction. The device is periodic in this direction, so this will be the size of the periodic simulation box in direction perpendicular to the transport. We choose here 20 nanometers, which yields converged current voltage characteristics for most OLEDs. If you choose a larger width, simulation times have to be longer as you simulate more particles. We have here a box for layers where you can define your material layers. You can add another layer by pressing the plus button. Within the material layer you can define the thickness of the layer. So this is in nanometers, so the first layer here is 10 nanometer thick. You can also define what kind of materials you want to have in your layer. At the moment there's one material in the layer. You could also add a second one by pressing the plus button and put in a concentration here. But in the first layer we only want the HTL, so we're going to leave this as it is. Morphology input mode automatic will in this case just create a cubic lattice, as we have not supplied any input from other NanoMatch software modules. If we would have supplied morphological input for an HTL, which we would have done in the materials tab, automatic would have automatically taken the morphology from this input and extrapolated it to create a bigger morphology with similar stochastic properties. If we want to force to do a cubic lattice, we can also choose here the option cubic. So for this simulation it would have the same outcome. So now we are going to add the other two layers of our system. The emission layer here with a thickness of 18 nanometers. The host materials with the host material and the emitter, concentration of 15%, and we add another layer for the ETL. Thickness we leave at 10 nanometers, and then we can define the attached electrodes. By default offers you 2 electrodes. You could also remove one, but then you wouldn't have a current, of course. As a coupling model we choose parameterized, but we leave basically the parameters as they are. But we might slightly reduce the coupling by increasing the inverse of the electrode wave function decay length. So this is by increasing this to 0.5, we will slightly decrease the coupling to the system. to have a little bit more efficient simulation. Most importantly, we have to set up the electrode work functions. The work functions injecting holes we will leave at 5 electron volts. The work function injecting electrons we will put to 2.8 electron volts. And with this we are finished defining our device. So now we are going to define the connectivity between materials by going to the topology tab. The setting max neighbors, which is short for maximum neighbors, determines for how many neighbors to a given molecule Lightforge calculates charge hopping rates. So if you have a very high number of maximum neighbors, let's say 150, Lightforge would calculate the hopping rates for a charge that is on a given molecule to its 150 nearest neighbors. Of course, most of these hopping rates would be very small, so the simulation time would be wasted. On the other hand, if you set this number too small, you might miss some significant hops, depending on your wave function decay length or the reach of your orbitals. For this simulation, since this is a cubic lattice, we will put 26 maximum neighbors. So this is the first coordination cube. This means you cannot basically tunnel through a molecule to the next molecule, but you can hop to all neighboring molecules basically. Since this is a parametric simulation, our transfer integral source here is Miller-Abrams, which will allow us to define the parameters for the transfer integrals according to the Miller-Abrams rates. Other options here would be, for example, QP output. So if we would have calculated transfer integrals using quantum patch, we could directly load the transfer integrals from quantum patch here. So we choose Miller-Abrams. The next drop-down menu called FRET determines how first resonance energy transfer rates are computed. We use the setting automatically computed from material properties, so we don't have to think about anything. Lightforge will just use the values supplied in the materials tab for the different exotonic properties to derive the first rates. Another option would be here to use heuristic parameters, so we could put in first radii for different material pairings. Now we see this box here called pair parameters, and for every pair of molecule types that we want to connect, so for which hopping should be able to occur, we have to define one of these boxes. We have to add this group by pressing the plus button. So of course we want to have transferred between HTL and HTL, so we need a box for HTL and HTL. We want to have transport between HTL and host. We want to have transport between HTL and phosphorescent emitter. We need transport between host and host. We need transport between host and phosphorescent emitter. We need transport between host and ETL. We need transport between phosphorescent emitters and phosphorescent emitters. we need transport between phosphorescent emitters and the ETL, and last, transport between ETL and ETL. The transport parameters that we have to define are basically the parametric transfer integrals. So we can define them for hole transfer integrals, for electron transfer integrals, and for Dexter transport. So for each entry we have an inverse wave function decay length, and we have a maximum transfer integral. The unit for the inverse wave function decay length is nanometers. The maximum, the value for the maximum transfer integral is electron volts. So we will use this, basically the default values we will use here, except for the Dexter transport, where we usually have smaller transfer integrals than for electron and hole transfer, 1 to 2 orders of magnitude smaller. So we will just adjust here the entries for the Dexter transfer integrals for all the different pairs. So with this we have defined the connectivity for all our materials. Now we go to the physics tab, and in the drop down menu rates we will choose automatic, which will choose automatic rate equations for different kind of processes that are simulated, and we are gonna uncheck the box super exchange, which should always be unchecked if you use Miller-Abraham rates. Now we continue with the operation tab, in which we can define the parameters of the actual simulations, like external fields or temperatures. Simulations determines the number of simulations for each data point. So for example, given one electric field, we will now do 15 simulations in 15 different simulation boxes and average over the results. We'll do a DC measurement with a temperature of 300 Kelvin, and we will do a simulation at 4 different fields, namely 0.06 volts per nanometers, 0.07, 0.08 and 0.1 volt per nanometers. I will shortly explain to you why we choose these values. So we defined earlier the OLED like this. So we have these basically 2 effective electrodes at the level from doped injection layers rather, but since we apply them as electrodes in LightForge, there will be a very high built-in voltage, and the built-in voltage will of course lead to bending, so we have to compensate for that, as we would not have to do this if we would simulate the doped injection layers explicitly, but now we have to do it. So we basically calculate first the built-in voltage, which is the difference between these effective work functions. So it was 2.8 minus 5.0 electron volts, excuse me. This is the OLED we defined in the Device and Materials tab, and which we have seen earlier. We have these effective electrodes to emulate the injection from doped injection layers in terms of energy levels. However, in LightForge, these are treated as metal electrodes now, the way we set up the simulations. It would have been also possible to explicitly simulate doped injection layers. This is, however, computationally very expensive, so we choose to simulate the injection with these metal electrodes, but this will lead, as there's a big work function difference, to a large inbuilt voltage, which we have to compensate. So the inbuilt voltage is the difference of the work functions, which is here 2.8 minus 5.0 volts. So the field that stems from that is this voltage divided by the length of the device, which is 10 plus 18 plus 10 nanometers plus 2 times 0.8 nanometers, which is basically the distance, the default distance from the electrode to the edge of the devices. So this leads to an inbuilt field which we want to compensate of 0.055 volt per nanometers. So to this we add an effective field to actually get some drift in our simulations, and we add here fields of 5, 15, 25 and 45 millivolts per nanometer, which then results in fields of 0.06, 0.07, 0.48 and 0.1 volt per nanometers. So we enter here these values that we just calculated, 0.06 to 0.1 volt per nanometers. Since we have electrodes attached, we don't need any initial charges in the system, and we will put these entries for initial holes and electrons both to 0. Now we have to set up settings for the computational convergence. There are 3 ways to determine when the simulation terminates. Either when it reaches a maximum number of iterations, this is a max iterations, which is what we will use in this case, since this is a rather efficient OLED. 600,000 iterations should be well enough to converge the results here. So this will roughly take 5 to 15 minutes to simulate, depending on your computational resources, of course. We will set IV fluctuation to 0.000. Otherwise, this criterion could lead to an early termination of the simulation if the current reaches a steady state, but we don't want this, so we put the condition that determines what a steady state is to a very hard condition, so basically that we will just simulate until max iterations are reached. We could also set a maximum time, so if the simulated time would be here over 100,000 seconds, the simulation would end, but of course this is would not ever happen for this OLED. So with this we are finished setting up the operations tab, and we can proceed with the analysis tab. So if you want to change something at analysis tab, we have to check this box. And what we are going to do is we are gonna check this box Exciton lifecycle, which enables a detailed analysis of the different states the excitons in the simulation go through, which is very helpful to analyze the bottlenecks of your LED. And we will put this setting auto run start to 0.1. This means after 10% of the simulation time, Lightwatch will start collecting data for the analysis. So if you're not sure your system is in equilibrium, this number should be higher like it was before, 0.5. Then basically only the second half of the simulation data would be used for analysis, but since this OLED converges rather quickly in its steady state, we set this to 0.1 to have a bit better statistics for the analysis. The last thing we have to do is we have to allocate our resources. In order to do this, though, we'll go back to the operations tab first, and we will calculate how many parallel calculations we would like to do in the optimal case. So we have 4 different fields, and we have 15 simulations per field. This means in total we have 60 independent simulations. So if available, we would like to allocate 61 computer cores. If we don't have this many cores available, simulation will just take a bit longer. So to allocate these, we go to the resources tab, and depending on your resources, you have to put in of course different numbers here. If you have computing nodes which have 64 cores, you could just put in like 61 here, and that would be okay. If you have smaller nodes, you can, for example, allocate 2 nodes which 31 cores each, and for this simulation we will allocate a total amount of 64 gigabytes of memory. Now we will save this workflow, go to File, Save As, and we give it a name, Model for LED. With this, we are ready to run the simulation by connecting to our computational resource and hit the Run button. When the job is finished, we can download or inspect the results by going to Jobs and Workflows. And here we see a list of the jobs that we ran. So now this was the only job. The name is the same as of the workflow. So because I ran this earlier with a slightly different name, it's not model phOLED but a simple phOLED. So in your case it would be also model phOLED. And by double clicking these icons, I can access all the data which was created. If I want to download all the results, I would download a results.zip and unpack this, and there I have I would have all the results that Lightwatch creates. We can, however, also inspect the results here within the workflow client. We do this by right-clicking here the Lightwatch icon and click on Browse Directory, which opens this file browser. And now we will inspect some of the important results like in the file browser. So for this we go in the folder Results, which you would also download if you download results. Zip is basically the same as the results folder. So the results folder, it has 2 subcategories, experiments and material, which have additional subcategories. So we go on material first, and we can, for example, click on energy levels, and there we see then for the 4 different applied fields, we can look at the cross section of the device, the energy levels of the device. We can see in blue the LUMO levels, in red the HOMO levels. Here that's electron blocking layer, hole blocking layer, and the distribution of different energy levels. Black are the electrodes. So to go back, we do a right click here in the black and press back. So we go back to here and we press on experiments. I'm gonna show you how to check whether the simulation seems to be converged. We can do this in the folder current characteristics. There are many files. The file we are looking for now is called trajaxall.png, which is basically a plot of all these Trajac files. So this is a trajectory file for all our 60 simulations. Why 60? Because we have 4 fields and 15 simulations per field. If we now click on Trajac all, what we see here is basically the trajectory for the 4 different fields and for the 15 simulations. So in black we see the trajectories for one field, in red for another, and so on. And what is plotted on the x-axis is a cumulative charge displacement. The units are here the device lengths. So that means, for example, in this blue case, all electrons together during the simulations time, they cross the device 800 times. So this is you can definitely in steady state in this case. You can also see a simulation is well converged if you can more or less put a linear regression through it. Now these are even, the individual simulations are even basically linear functions. They will not always look like this. They can be very noisy for less ideal systems, but you should, if you cannot do a linear regression through, say, the second half of it, then the current values that are calculated would not be reliable. So this is basically how you can roughly check the whether what you simulated was actually in a steady state. On the y-axis it's just the simulation time. So we go back again, and now we can look at the current voltage characteristics. For this we click simply on IV PNG, and we see here the current voltage characteristics of these OLEDs in ampere per square meter. So take care, this is not milliampere per square centimeter, but ampere per square meter in this case. And we see basically a typical current voltage characteristic for an OLED. And we go back, and we can also look at the IQE, the internal quantum efficiency. For this we go to IQE.png, which plots the internal quantum efficiency against the current in milliamps per square centimeter. We see we have a very high internal quantum efficiency of almost 80% for the smallest field, and then we have a steep efficiency roll-off. At the high currents we have only an internal quantum efficiency of 10%, so this would mean maybe 3% if you also take into account outcoupling. Now we will look at some more results. We will analyze charge carrier balance and see why the quantum efficiency is that it is. To do this, we go to the folder particle densities. Again, there are many files here. So what we are gonna look at is the file quenching density. You see you have quenching density 0 PNG, 1 PNG, 2 PNG and 3 PNG. This is for the 4 different fields. We're gonna look at it now for the 0 for the smallest field. The x, that's the device length, and y, you see in the lower plot the average distribution of electrons and holes in the system. So in blue, electrons, in red, holes. You see you don't have a lot of holes. 0.06 here is the amplitude at the same time. And at the top you see basically where quenching occurs, spatially resolved, so it's mostly in the emission layer and kind of evenly distributed. Now if we are interested, if you look at the same plot for a very high field, so going from the 80% quantum efficiency to the 10% quantum efficiency, we see much higher charge densities. Here we see we have average charge densities in the emission layer of around 0.25 here. In this bin per 20 times 20 nanometer cross section, which was our device length, and all the quenching basically occurs where we have the charge. Now we can analyze, look at the analysis of what kind of quenching happens by looking at the plots which are called exciton decay density. Again, we have the plots here for 0, for 1, for 2, and for 3. So we will look at it first for 0, and we have then 4 versions. We have 1, 2, 3 total. This is for the different materials. So total would basically show us summed up over all materials, basically the different exciton quenching events. This also includes radiative decay, so this would not be called quenching, but it's also included in this plot. And it also includes shows where excitons are recombined, so it's a recombination here. You see basically we have lots of recombination, kind of evenly distributed in the emission layer, and lots of radiative decay evenly distributed over the emission layer, and here negligible the other kinds of events like TTA and other things. Now going back, we can for example look at this only for species 1, which should be the host, and we don't see a lot. We have some recombination on the host, but nothing else, which means we have a good energy transfer from the host to the emitter. If we look on the 2, which should be the emitter, we see that this is basically where most of the music is happening, which it looks rather similar to the plot that we saw before, where it was summed up over all molecule types. Another interesting analysis we can find in the files Exciton lifecycle.html. Again, we have 4 different files, 1, 0, 2, and 3, corresponding to the calculations for the 4 different fields. Let us open Exciton lifecycle _2 for the second strongest field. This pie chart shows the life cycles the exciton in our device go through. We start reading it off in the middle, where the excitons are created. You can see that there are 2 different segments and another tiny one. The small segment corresponds to recombination to a singlet, and the larger segment to a recombination as a triplet. So going outward from these triplet excitons, we can read off what happened next to the given fraction of excitons. The outmost tile shows how this fraction of excitons was destroyed. In the case of this red tile, this corresponds to TTA, as we can read off in the inset or on the legend on the right. If we look in the inset, the block life model type describes the distribution of, in this case, TTA events over different species of molecules. In this case we have only molecule type 2, which corresponds to the phosphorescent emitter, as it was the third molecule that we defined, starting to count from 0. Below we see the box life state. This corresponds to the spin state in which the excitons were destroyed. So here we also, all of the excitons that were tracked, in this case 1026, were in spin state 4. 4 corresponds here to a triplet, 3 would correspond to a singlet. So now looking at other kind of events. We see here a significant percentage of the excitons was quenched by exciton polaron interaction. In green here we have a direct radiative decay due to phosphorescence. Blue is a spin conversion to a singlet, so the exciton continues to live on. There's another spin conversion to a triplet again, and then here we have again kind of a miniature diagram of the 3 processes we saw before: exciton polaron quenching, TTA, and radiative decay. The same we can read of these diagrams for the singlet. We have the recombination as singlets here. All the singlets then undergo intersystem crossing. We can see all of them undergo this process on molecule species 2, so on the phosphorescent emitter, which has of course very effective intersystem crossing. Afterwards we have triplets again, indicated by a life state type 4, and again then the molecules are destroyed either by radiative decay, TTA, or exciton polaron quenching. Move charge here indicate that this is exciton polaron quenching due to a Dexter type of interaction. So overall we see we have efficient intersystem crossing here, and then all generated triplets either decay radiatively, are quenched by TTA, or are quenched by a exciton polaron interaction, almost in equal proportions. Now we can go back and look at the same kind of diagram for one of the weaker fields, Exciton lifecycle 0 HTML. And we see that if we hover the mouse here over the green tile, that the chunk of radiative decay is significantly higher than before, as we have lower charge densities at the lower fields, and consequently also lower triplet densities. Let us see what is happening with this pink fraction of the triplets. We see move flip exciton faster. This means that we have a faster energy transfer from a triplet to a singlet. This is possible because this is a phosphorescent molecule, and because the singlet triplet gap for the molecule is not that big. But then if we go to the next tile, immediately we have a back conversion due to intersystem crossing on the acceptor molecule, and again the majority of the triplets decays radiatively. If we go to the next tile, we have immediately a back conversion due to intersystem crossing. The majority of the newly generated triplets then again decays radiatively. Now let us go back. Another interesting analysis you can find in the folder Exciton mole pairs. Exciton mole pairs. There you have for the different kind of material combinations, so ETL phosphorescent emitter, host phosphorescent emitter. You have a transport count for different for the excitons. So you have an energy transfer from your host to host, and you have this happens through different kind of Dexter transfers and through a Förster transfer here, and you for the different distances which are possible between these molecules, you can see how often this kind of transport event occurs, so you have a very detailed analysis of what's actually happening in your system. Another interesting analysis you can find if you go back to the materials folder, and there's a folder Exciton separation, also for the different material combinations and different fields. If you click on one of these, it will show you the energy costs for charge separation from an exciton. So there are 4 different ways this can happen. I mean, either if you have an exciton on a phosphorescent emitter, an electron could go to the host, or a hole could go to the host, or the other way around. If you have an exciton on the host, an electron could go to the phosphorescent emitter, or a hole could go to the phosphorescent emitter, and these are basically these 4 curves. And in this case you see all of these have positive energies, so it is very unlikely in this case that when an exciton was formed that it will dissociate again, but in many cases you will have exciton dissociation, and you could see this in this plot, or rather you could see the likelihood that exciton dissociation happens. Also, if you're interested furthermore in different analysis, you can look at the actual exciton transfer rates. If you go on Förster, here again in the material folder, that will show you for the different species combination the different transfer rates. So normal Dexter transfer, for example, between HCl and HCl would have a distribution like this. So this is discrete because we have a cubic lattice, so these are the only possible distances between host materials. You see you have quite high transfer rates, but also for different kind of Förster Förster processes. Here S1, S1, and then for the different species you also have S1, T1, or T1, S1, so hyperfluorescence kind of process for all the different material combinations. There are a few other results you could look at, but these are the most interesting ones to analyze the efficiency roll-off in OLEDs.